So, last class we are discussing the solution of unconstrained optimization problem using Newton's method, and we have seen there are two drawbacks are there. One drawback is there that you have to each iteration you have to find out the Hessian matrix or second derivative of the cost function or objective function, and that must be at each iteration must be a positive definite matrix, and this is the first drawback. And because this condition must be satisfied, because we are going over the descent direction. So, that each iteration from kth iteration to k plus 1th iteration, the function value should decrease. That is the condition that so Hessian matrix must be positive definite. Another drawback is there, each iteration you have to do the inverse of this matrix whose dimension is n cross n. That inversion, Hessian matrix inversion, you need it at each iteration, and n is the small n is the number of variables involved in the decision objective functions. Then we have seen that this problem can be overcome by using quasi Newton's method. It is similar to Newton's method, only the inverse of the Hessian matrix at each iteration is replaced by a some matrix S suffix k, kth iteration. That matrix is updated at each iteration that you have to update. Then how you have to update that one, we have explained this one, but now we will derive that expressions. If you recollect this one, that we want to replace in the Newton's method this inversion, that means Hessian matrix inversion, by a positive definite matrix x of k suffix k, and then next is x of k, how we have what is called updated this one. We have seen that this is the updated expression. We have shown you that x k plus 1, if you see this one, x k plus 1 update x k, then these things you have to calculate. Delta k is nothing but a that successive 2 iteration, that x difference of x values. Gamma k is the successive 2 iteration, the gradient of objective functions, difference of gradient of objective function. This way you have to update. How we got it this expression, that we are going to discuss now, and the derivation is based on that our concept like this way, that the function value, let us call f is a function which is a function of x and variable. The function difference of function value at 2 successive points carries the information of derivative of the functions. Similarly, the next second derivative, that gradient of the function at 2 successive points carries the information of the second derivative of the function, that means Hessian matrix information carries. Based on this one, we have retained that one, that Hessian matrix of the function at k plus 1 instant or the iteration is equal the difference of two gradients at successive points, 2 successive points x k plus 1 and x is equal to x superscript k. This difference carries the information of the second derivative of this function, that means Hessian matrix information. If you multiply it by that change in, that is variable change in difference in that variable change, if you multiply it, then this is equal to expression, you can write it. From there I rearranged yesterday, if you see x k plus 1 minus x superscript k is equal to this matrix inversion, then Hessian matrix inversion. So, I mentioned earlier that in Newton's method for solving the unconstrained optimization problem, this is creating problems. First thing, delta square f Hessian matrix must be positive definite, that is. Next is this inversion is always exist. When the number of variables is very large, the computation burden involved here is much. So, this one we are not taking the inverse, we are replacing this one by a matrix x k plus 1. Again, so this we are replacing x k plus 1. Now, see this one, how this x k plus 1 is, that x of k each time it is updating. So, that is we will discuss now. Now, look this let us call this expression, that is what we will write it, this expression you write this equation number 1, last class we have written this is equation number 1. Agree? So, now question is given x k, then x k plus 1 x k plus 1 can be obtained using correction formula, and that correction formula is based on the rank 1 type or rank 2 type correction formula. So, various type of correction formula is available, that means one may be a correction type of order 1, rank 1, rank 2 another. So, you can write various correction formula have been developed in the literature, most of which are of the type 1 or type 2. Agree? So, let us see. So, now we can write x k plus 1 is equal to x k. So, this now I am updating x k, I know x k plus 1 at kth iteration, what is the Hessian matrix inversion at k plus 1th iteration, that I am finding out by S k plus adding a correction term w delta of suffix k, where this delta of k is a matrix of same dimension of x k, and x k dimension, as you know, it is n by n, this matrix also n cross n matrix. Agree? And that matrix is a positive definite matrix, this. Agree? So, that matrix of rank 1 or rank 2 or rank 2. The simplest choice of delta k one can take like this way, the inner product of the outer product of any two vectors, which is not a null vector. So, I can define delta k as a special choice of delta k like this way, alpha k u k and u k transpose. This is the inner product of vector u k at kth iteration, u k any vector you have considered multiplied by u k transpose. So, this product of this outer product of the vectors u k and this same vector outer product, if this is a matrix of dimension n cross n, where the u k dimension is n row 1 column. Agree? And alpha k is a scalar quantity whose value is greater than 0, that is scalar quantity, scalar greater than 0, this. So, this is the choice of this one, and this matrix, if you see this is always positive semi definite matrix. So, if you add it with a positive definite matrix, another positive semi definite matrix, results will be a, at most it will be a positive semi definite matrix of that one. Agree? Or no, sorry, the result will be a positive definite matrix of that one. Agree? Because this is a positive definite matrix. Now, a positive definite matrix add with a delta k, which delta k is positive semi definite matrix, results will be a positive definite matrix. This matrix is positive definite matrix, and this is positive semi definite matrix, and that results will be positive definite matrix. So, this with this one, let us call this equation is I am considering this equation number 2, and this is the equation number, this equation is equation number 3. Agree? From 2 one can write it, from 2 x k plus 1, that what I mentioned is that is a symmetric matrix, symmetric if S k is symmetric. And see, when you take the outer product of two same vectors, this results is you will get a symmetric matrix. Okay. So, symmetric matrix plus symmetric matrix is a symmetric matrix of this one, that is from 2 you can see this one. Then note the what we have defined, delta k is nothing but a the change in decision variable value at k plus 1th instant minus at kth instant. So, that is we are denoted by delta k symbol. Similarly, gamma k, this gamma k is the difference of gradients at two successive points. What is the successive point? Delta f x is equal to superscript k plus 1 minus delta f x superscript of k, this derivative. So, let us call this is equation number, last equation we have given the number 3. So, this is 4 and this is 5. Again our main job is here now replace that u k and alpha k, this u k and alpha k replace in terms of the information delta k and gamma k. That is our next step, how to replace it. Aim is to replace that our alpha k and u k in equation 2 with delta k and gamma k, this. So, so how will you do this one? Now, see this equation number 1. This equation number, recall the equation number 1, this equation number 1. If you recall equation number 1, then I can write it x subscript k, and this is what we have denoted by this one, gamma k, the change in the what is called gradient of the function at two successive point change we have denoted by gamma k. So, I can write this is gamma k is equal to delta k. See this one, if you take this side, it will be a delta k. So, I can write it this expression from equation number 1. So, now what is x k plus 1? This I can write it x k plus delta k, that is the what we have considered, x k plus 1 we have considered like this way, into gamma k is equal to delta k. Agree? So, now I can this if I take it that side, x k gamma k in right hand side. So, I can write it delta k gamma k is equal to delta k minus x k into gamma k. This is x k. So, that one we can write it, and one can write it this one, because you know what is delta k I have considered. Delta k is nothing but a alpha k outer product of same matrix u k. So, this I can write alpha k u k transpose, this is delta k, into gamma k is equal to delta k minus S k gamma k. And note this one, what is gamma k? Gamma k is nothing but a difference of the gradient value at two successive points gamma k. So, it is a vector of dimension n cross 1, and this is also dimension u k transpose is dimension 1 cross n. So, this quantity, these two product are a scalar quantity. scalar quantity. Agree? Now, both side I multiply it by gamma k transpose, both sides, and alpha k is also scalar. So, if both side you multiplied by gamma k, then left hand side alpha k, then gamma k transpose u of k, then u transpose of gamma k is equal to, because I both side I multiplied by gamma k, this equal to delta k minus s of k into gamma of k, gamma of k, this is gamma of k. Now, this you see this is a scalar, and inverse of this scalar is that one, this is also scalar. So, what is this value is later, let us call it is 5, that is also 5 if you take inverse of this scalar quantity, scalar. So, I can write square. So, alpha k, this is like alpha k, I can write u transpose u k transpose gamma k whole square, 2 scalar quantity square I can write is equal to gamma k transpose delta k minus x k gamma k. So, let us write it, this is equation number, last we have gone up to equation 5, then you can recall that one is this, you can consider equation number 6, agree? Then you can call this is equation number 7, that one, agree? And that is the identity, you can see one can write it this identity without any problem. Note this identity, note this identity. What is this identity? Alpha k u k transpose, and this the whole thing is nothing but, if you see this is nothing but a delta k we have considered, and alpha k is the scalar quantity, agree? That is what I mean is a scalar quantity. If you recollect that our alpha k definition, that what we have just considered, alpha k is a scalar one when you have defined the your that is delta k, this is alpha k is a scalar and this is a matrix. So, delta k is matrix, this we can write it, the same thing we can write it alpha k, this we can write it, then we can write it u k, that one as it is, then you are writing u k transpose gamma k, then gamma k transpose u k, then you are writing u k transpose this one, agree, into alpha k, agree, divided by you see alpha k u k transpose gamma k, agree, gamma k transpose u k. So, they say I told you gamma u k transpose gamma k is a scalar quantity, this is a scalar quantity, scalar. So, this is a scalar. So, this is this scalar, same thing, same quantity I am written down. So, you can cancel it, agree. So, this alpha and this alpha you can cancel it. So, what is left? Alpha k u k transpose, the same thing, but we have written into a this and these are the identity, either you write this one or you write this same thing, but this quantity whole, because I can divide, this is a matrix, right hand side this quantity from here to here must be a matrix, and this divided by a scalar quantity. You see this is a scalar and this is a scalar, and alpha is, we have considered alpha is a scalar. So, I divide the matrix by a scalar quantity. So, these are the identity you can say. So, now from 2, what is the equation number 2? If you just say the equation number 2 here, this equation, what how to update that x k plus 1 iteration. So, 2 if you take that side x k plus 1 minus s k, it will be equal to delta k. So, I am writing x k plus 1 minus x k, and x k you know what is it? The inverse of Hessian matrix at kth iteration, at k two successive points, k plus 1th iteration, the inverse of Hessian matrix, and this is the kth iteration inverse of the Hessian matrix. The difference of this one is written by, you see that one, equation number 2, this difference of this delta k and delta k. So, I can write it that the value of delta k now here. What is the value of delta k? From equation, from this equation, this expression I can write it, the whole expression. What is, because this nothing but a that one, just now we have shown it. So, you can write it alpha k u k, then u k transpose, again this I am writing into gamma k. So, these 4 quantities 1, 2, 3, 4 quantities in together I am writing, agree this up to this I have written. Remaining is I am writing gamma k transpose u k transpose alpha k, agree. So, this, and you can see here this is nothing but a transpose of that one, that quantity is transpose of this quantity is transpose of that one, or vice versa. So, divided by that scalar quantity, and what is this quantity? This is a scalar, whatever the value of this one and this value are same. So, I can write it square. So, alpha k u k transpose gamma k whole square, because what is the value of gamma k transpose u k is the same value of u k transpose, because transpose of scalar quantity is same quantity. So, it is scalar quantity, and this quantity you see, this is what you can easily verify this one, this is a scalar quantity, again, and this is also scalar quantity. These two scalar quantity is a scalar quantity. U k is a row vector, sorry, column vector. U k is a column vector whose dimension is n row 1 column, and this is the transpose of this one, that will be a row vector. So, row vector, column vector post multiplied by same matrix with a row vector, that results is a matrix. So, I am getting this one, again. So, from 6 and 7, that 7 expression you see with this one alpha k u k gamma k square, this quantity I can write by replace by this one, denominator expression I can replace by that one, again or you can replace by that equation number 7. So, using equation number 6, say 6 alpha k u k transpose gamma k, alpha k u k transpose gamma k, I will be replaced by that quantity. So, using equation number 6 and 7, using equation number 6 and 7, or from 6 and 7, we can write x k plus 1 minus x of k s, this is s k is equal to, I am replacing from 6 and 7 delta k minus x k gamma k into delta k minus x k, this is s k gamma k whole transpose, divided by gamma k transpose delta k, agree, minus u k, and this is gamma k, agree. So, that what is this value? Just see this one, this gamma k transpose x k, this is a delta k minus this I am replacing equation, see this one, here alpha k u k transpose gamma k equation to gamma k transpose delta k minus x k, then gamma k x k and gamma k. So, this is x k delta k minus x k into gamma k. S k is a matrix multiplied by vector, column vector is a vector. So, vector minus this vector and multiplied by another row vector. So, it is a scalar quantity. So, this I can write it. So, therefore, I can write x k plus 1 is equal to x k plus delta k minus x k gamma k and that transpose delta k minus x k gamma k whole transpose divided by gamma k, this gamma k transpose delta k minus x k gamma k this quantity. So, you see at each iteration now we have derived, at each iteration the inversion, that is Hessian matrix inversion, is replaced by a matrix equivalent matrix x k, and next iteration x k plus 1, that means inversion of Hessian matrix at k plus 1th iteration we can obtain knowing the previous value of x k and this compute that one, and this one you know delta k is the difference of the values of the decision variables x value difference at two successive point k plus 1 and k to 1, and gamma k you know the difference in gradient of a objective function at two successive points, the difference this. So, I can compute iteratively this one for k is equal to 0, k is equal to 0, 1, 2, 3 dot dot in this way. So, each iteration if one will compute recursively like this way, I am avoiding the inversion of a what is called that Hessian matrix inversion when you will compute the solution of optimization problem using the Newton's method. Okay. And when you will replace them by a matrix this and recursively we are calculating S k plus 1 agree in place of inversion of a matrix, then we will call it as a quasi Newton's method. It is like Newton's method only, the different way we are calculating. So, one of the advantages is disadvantages look at this point. This is a scalar quantity, this whole thing is a scalar. One must be careful that denominator part should not be very small or 0. If it is 0 or very small, this quantity will blow, agree, very large value will come. So, that is the one disadvantage of this rank 1. This problem can be, this derivation is based on the rank 1, because we have considered, if you recollect, that delta k we have added with x k by choosing the delta k matrix like this way, a vector outer product of same vectors u k transpose, and that rank is 1. On that basis we have derived. So, if this is very small or very small or 0, then you cannot apply these things. Okay. So, one can, the alternative way is you go for rank 2 for choosing the delta k. So, this is the one disadvantage. Advantage is there, you do not need to check the gradient direction, because that direction, that is what we are checking, the gradient direction, which in turn we got that what is called Hessian matrix must be positive definite matrix. It is not necessary in this case, because it is automatically once you see this one, once you have selected at k is equal to 0, S of 0 is positive definite matrix, any positive definite matrix of that one, and this I told you delta k, that is what is, this is nothing but a delta k, the delta k expression you can write it like this way. This is always a positive semi definite matrix, and in turn that matrix is a positive definite matrix, you will get it. Okay. So, the results always it is guarantees that this is a positive definite matrix. So, you need not to check the what is called descent direction of a function at each iterations. So, that is the one advantage of this Newton's method, and due to this one it is widely used for optimization what is called unconstrained optimization problem. That method quasi Newton method is widely used due to this advantage. So, next we will see, so far we have discussed that how to solve that what is called unconstrained optimization problem by using the numerical techniques, or directly you can solve it. Let us call unconstrained optimization. How will you solve it? First, the gradient of this vector you assign 0 and solve it, find out the what is called stationary points. Then you find out the second Hessian matrix of this one and check whether the Hessian matrix is positive definite or negative definite or not. Check it and you will be able to conclude that function is minimum or maximum. If the Hessian matrix is positive definite, then the function is a minimum function, value of the function you achieve the minimum at that stationary point. If the Hessian matrix is negative definite, agree, by analytically if you solve, if you get it negative definite, this means at the stationary point corresponding to that stationary point, the function value you will get the maximum. So, let us go next is that constraint optimization problems, how to solve the constraint optimization problems. So, next is your optimality, and once you see knowing these algorithms, and one thing I just forgot to tell you that what is called steepest descent method, the convergence rate is linear, means order 1. Whereas, in conjugate gradient method, the convergence rate is between 1 and 2. Order 1 means what? It is a linearly, it is approaching to the what is error is decreasing, or it is approaching to the function value is approaching to the minimum value of this function linearly. Whereas, in Newton's method, the convergence rate is quadratic. In other words, the convergence rate order is 2, and similarly that what is called what is called Newton's method is order convergence rate is much faster than the steepest descent method, and its order is 2. So, next we will consider the optimality condition for constraint optimization problem, optimality conditions for constraint optimization problems. Agree? So, let us, if you recollect our first lecture, we have discussed that what is the basic structure or mathematical formulation of optimization problems. Agree? Now, we are going for constraint optimization problem basic structure. If you see generalized constraint generalized constraint optimization problem. Most of the practical problems you see, there must be constant real time real world problems, there must be constraints, and not only constraints, then equality constraint means, and what is called inequality constraints. Agree? In addition to this one, there is a side constraints are there. Some of the variables cannot be positive, negative, all these things that we have discussed at length in our first lecture or second lecture. Agree? So, let us call what is the generalized optimization problems that minimize. If you recollect, minimize f of x, and x dimension is n cross 1, which you can write it as x as a n variables. So, our decision variables are n variables are there. We have to minimize these functions. So, let us call this function I am getting to equation number 1. Agree? So, subject to, I just recollect our problem, that subject to equality constant. So, we have a h I which is a function of all decision variables, may not be, some of the function may be few decision variables x 2, x 3 dot dot x n, and these are the all equality constants, agree, and this I varies from 1 to dot dot p. So, there are p equality constants is there with the optimization problems, subject to how many, I is equal to 1, h 1 is equal to 0, h 2 is equal to 0, dot dot h p is 0. So, we have a p equality constant and also inequality constants g j, which is a function of x 1, x 2, x 3 dot dot x n, agree, x n is equal to 0, and that we have a x 1 2 dot dot m, small m. So, we have a m inequality constant, sorry, this is inequality, we have a m inequality constants are there. So, our problem is minimize this function subject to these constants, agree. So, this is equation number 2 and this is equation number 3. If the equation number 2, 3, 1, 2, 3 are all function of linear functions, then we will call linear programming optimization problems. Otherwise, it is a nonlinear optimization problems. Any one of these is nonlinear, that we have discussed earlier also. So, so we have a linear optimization problem, may be nonlinear optimization problem, may be. Let us see about the constants, get some idea about these constants. Suppose we have a problem like this way, minimize example just to explain the constant of minimize f of x, and x is a, we in our case 2 variables dimension is. So, it is a x 1 minus 2.5 whole square plus x 2 minus 2.5 whole square. Okay. Our problem is minimize this quadratic functions, agree, subject to g 1 of x, which is a function of x 1 and x 2, agree, and is equal to 2 x 1 plus 2 x 2 minus 3 is less than equal to 0. Let us call we have a only one inequality constant here. Please note that when there is a equality constant is there, we are using h, small h. When there is a inequality constants are there, we are using the small g, that is we will use this notation throughout our discussion. So, this is the problem and this is you have to optimize this one. And if you see the graphically this problem of that one, agree, and another constant also you can see g 2, which is a function of x 1 and x 2, agree, is equal to minus x 1 less than equal to 0. Another is g 3, x 1 x 2 is equal to x 2 greater than equal to 0. Just you can see this one. So, this, what is this one? Let us see this point g 2 inequality constants, minus x 1 is less than equal to 0. That means, it indicates the x 1 value is always positive. So, this in other way I can write it, this one I can write it also g 2 of x 1 and x 2, I can write it is equal to x 1 greater than equal to 0. Because this expression is showing that this quantity, that means this quantity always less than 0. When it is possible? When x 1 is greater than 0, greater than equal to 0. So, this I indirect or in other words I can write this one. So, let us say that constant g 2 in place of this one I am writing that one, x 1 is greater than equal to 0. That means, this indicates which region, that x 1 is always positive. So, I can see the our region of x 1 is that side, okay, this side this. So, if you consider this is our x 1 and this is our x 2. So, this indicates that x 1 greater than 0. So, x 2 greater than 0, the third inequality condition G 3 means x 2 value is always positive or 0. So, this indicates that region, that is region. So, the first quadrant G 2 and G 3 indicates the first quadrant, our design space or design variables must lie in the first quadrant from G 2 and G 3 I can say this. Now, what is this equation, that first constraint, inequality constraint, that you just draw the line that 2 x 1 plus 2 x 2 minus 3 equal to 0, draw the line first, then I will decide less than 0 in which side of the line or greater than 0 which side of the line. So, if you draw equal to, then x 1 is, if x 1 is 0, then x 2 is becoming, x 1 is 0, 2 x 2 minus 3 is equal to 0 means x 2 is 1.5. Let us call this is 1, this is 2, this is 3. So, 1.5 is here, this point. This is the equation of this straight line, this. Okay. Then, when x 2 is 0, then x 1 is again 1.5. This is 1, 2, 3 and 1.5 is here, 1.5 is here. So, this is equation of straight line. So, I can draw it this one, this is, I cannot extend because it does not valid, because x 1 x 2 value is greater than 0 means in first quadrant. So, you cannot go like this way, that valid up to this region, design space is only first quadrant. So, this indicates that equal to 0 G 1, that means G 1 is equal to 0 any point on the line, but we have given that G 1 is less than equal to 0, agree, less than equal to 0. That means, which region, the G 1 less than equal to 0, that should be what is called in this region, that is this region is G 1 less than 0, less than equal to 0. When equal to, that is when G 1 equal to 0, that is on the line. When G 1 less than 0, that means in this region, the whole region. If you see just straight line, if you extend it, the whole region G 1, the whole region of that one, the whole region G 1 of x 1 x 2 less than equal to 0, either on the line or this. But our G 2 and G 3 are telling that our design variable x 1 and x 2 lies on this first quadrant. So, we cannot go outside this first quadrant. So, our design space or design variables must lie within this triangle. Agree? Now, our what is our problem? Our problem is to minimize that one. So, if you see this one, this is nothing but a equation of a circle whose center is 2.5 here, 2.5 comma 2.5. This is our center of the circle. Now, it is obvious, you see minimum value of the, suppose these constraints are not there, what is the minimum value of the function at centers, means 0, but we have a constraint. Now, if you increase the size of this, that is that with the center, if you just the function value you to increase it, suppose I put it a function value, this is some value function there, but this does not satisfy our constraints. Agree? These three constraints combinedly we have shown, this is our space where this our x 1 x 2 must lie. So, now next our if you go on increasing, so our minimum value of the function from geometrical point of view one can say lies on the straight line, on the straight line. How? From there you draw a circle which will touch this straight line. Okay? And beyond that, if you want to increase the size of this circle, it lies no doubt on the design space or the design space, but function value is increased. This is not the minimum. Minimum of it will be what? Which will touch this line. Let us call that one. So, this is O point, this is P point here. So, now you can easily find out what is this point at which this circle will touch, and that point you will get the minimum value of the function. It is a simply geometry concept. Agree? So, when it will touch this one can find out from geometry point of view from this point to on this line what is the perpendicular distance, you can find out. Once you know the perpendicular distance of this one, you can find out what is the coordinate of that one by using some geometry of this one. So, once you know this coordinate, immediately you know what is the function value, put the value of x 1 and x 2. So, I will just give you these hints that OP you can find out. If you write it OP, the perpendicular of distance this one by coordinate geometry distance 2 x 1, you see this equation plus 2 x 2 minus 3 divided by the coefficient of a x plus b y plus c is equal to, you know, the distance from any point is, that value is 2 square means 4 plus 2 square 4, put the value at x is equal to x 1 is equal to 2.5, from this point we are drawing, and x 2 is 2.5. If you find out this one, that value will come approximately, not approximately, it will come this one x p. Now, this line, this OP and this straight line are perpendicular to each other. Agree? And you see, you can easily find out the slope also, if you like the slope of that one also. Agree? What is the slope? That means, if you draw this one, this and this coordinate you do not know, let us call it is x 1 bar and then x 2 bar, this point. So, immediately you can find out this is from here to here is x 1 bar, y x 2 bar, this is, you know, 2.5. So, it is 1.5 divided by this is, you know, 2.5, this is 2.5, this is x 2 x 1. So, 2.5 minus x 1, so this two ratio, this by this ratio is same, means 1. So, the slope I know this is 1. From there you will get it one expression x 1 bar and x 2 bar expression. So, I can write it, if you see 2.5 minus x 1 x 2 bar minus 2.5 minus x 1 bar is equal to 1, that implies x 1 bar is equal to x 2 bar. Agree? So, this coordinate x 1 x 2 are same. Next, what you will do? This coordinate must satisfy this circle equation. And what is the circle equation? If you see, the circle equation is our x 1 minus 2.5 whole square plus x 2 minus 2.5 whole square is equal to the distance we got it. If you recollect this one, OP distance is 7 by 2 root 2, 7 by 2 root 2, 7 by 2 root 2 whole square. So, put this value x is equal to, because it satisfy at x is equal to x bar and x 1 bar x 2. So, if you put this value in this case, so it will be x 1 bar minus 2.5 whole square plus x 2 bar minus 2.5 whole square is equal to this quantity. So, solve these two equations. I know x 1 is equal to x 2, agree. So, x 1 we know x 1 is equal to x 1 2 is equal to x 2 bar, then you can find out x 1 bar. From this one you can find out x 1 bar is equal to x 2 is equal to that value will come, x 1 bar will become 1.26. Please check it, just in this expression you put it, it will get it. So, and we know, and physically this is the what is called these three equations, inequality constants I just drawn in a graph and shown without solving any what is called optimization technique, all this thing physical geometric concept of view, I find out what is the point, at what point the function value will be minimum, that is one. But next we have to do it through what is called by analytically. Now, look at this expression. If you recollect this one, in general let us call we have a one expression is there, x 1 x 2, that expression, and that expression is what in your for this specific problem, see that one 2 x 1 plus 2 x 2 minus 3 is less than equal to 0. So, this quantity I can always write in equalative constant form. But what does it mean? This quantity is less than 0. That means, if I add some positive quantity with this one, then I can make it this is equal to 0. So, I am writing now that our inequality constant is now converted into equality constant. How? See this one, plus I am adding one positive term, because this is less than 0 means negative term, I have to add some positive term to make this is equal to 0, agree this. So, any inequality constants are there, I can always write it into a this plus some positive quantity, you have to add this quantity, that is what quantity is greater than 0 or equal to. Now, look at this one, when s is equal to 0, that means this satisfies the equality constant, agree, that satisfies the equality constants. So, so any inequality constant now I can convert into a equality constant by adding s 1 square, which is a greater than equal to 0, and it cannot be negative. If it is a negative, s 1 square is negative, that means it indicates this quantity is G 1 is always negative, this quantity, and if it is coming negative, that means this violates the our constant given that constants. So, that s 1 square this should be always greater than equal to 0. Now, so now question is that we know at this moment how to solve the unconstrained optimization problems. So, if you have a what is called general problem that we have mentioned it, minimize the function subject to equality constant and inequality constant, and inequality constant we know how to convert into a equality constants. So, now next question is, if we can convert the constant optimization problem with equality and inequality constants, and inequality constants we can convert into equality constants, then the problem is if you can transform that unconstant optimization problem into a what is called constant optimization problem into unconstant optimization problem, then we can solve our problems as per our we have considered earlier. Because unconstant optimization problem we know how to solve it either numerically or what is called by analytical method. So, let us see this one how to convert. One way conversion is quickly, if you see this one, minimize same problem f of x 1 x 2, that x 1 minus 2.5 whole square x 2 minus 2.5 whole square subject to h of 1, only one equality constant is there, is equal to minus 2 x 1 plus 2 x 2 minus 3 is equal to 0. It is only one equality constant is there. So, how to convert this what is called constraint optimization problem, how to transform into a unconstrained optimization problems. One can do like this way, you see I will find out x from here, x 2 is equal to what, minus 2 x 1 plus 3, if you take this divided by 2 is nothing but a half, this 2 to cancel, it is a minus x 1 plus 1.5. If you put this value of x 2, put the value of x 2 in this objective function, now it is a function of x 1 and x 2 is a function of, I can write this is a function of x 1. So, it is a function of x 1, agree, which I can write it now. If you just put this value of x 1 minus 2.5 whole square, then in place of x 2 I will write it minus x 1 plus 1.5 minus 2.5 1.5 minus 2.5 whole square. Now, you see this constant I have forced the equality constant I have forced in objective functions. So, now it has become a unconstrained optimization problem. There is a unconstrained optimization problem. So, this problem we can solve what we have discussed earlier, this one. Similarly, inequality constant is there, I have just mentioned how to convert in equality constant and then proceed in the same manner. So, next class we will discuss more general in inequality constant also along with the equality constant, how to convert what is called equality constraint optimization problem into unconstrained optimization problems. Thank you.